I'm Caitlin O'Quinn. I'm a student at the University of Texas at Austin, and today I'll be talking about the tailoring of calcined impure clays for improved performance. My advisor is Dr. Marie Younger of the University of Texas, and we're in a joint project with Dr. Susan Bernal at University of Leeds. With that, I'd like to thank our funding organizations of National Science Foundation and also the UK Engineering and Physical Sciences Research Council. I'd also like to thank Dr. Alistair Marsh, Dr. Yuvraj Dandapani, and Dr. Saif Alshmaisani for their help and assistance with the study. A little bit of background for the session. The use of supplementary cementitious materials, or SCMs, reduces clinker content and the contribution of CO2 from cement manufacturing. Fly ash and slag are currently the most used SCMs, but they're limited in their availability and quality. The moderate purity clays are available across the US and globally and can be calcined and used as SCMs. So these moderate purity clays may even be better than pure clays like metakaolin for use in concrete because of their impact on workability. So the objectives thus far in this study were to collect and characterize a variety of impure clays sourced from North America, particularly the US, and to evaluate the chemical reactivity of these clays using the R3 test, and also to gain workability insight with the minislump test. The materials procured are a combination of two commercially calcined or industrial calcined impure kaolinic clays. So these were sent to us from the supplier already calcined. And then we were also obtained raw clays from a wide geographic region of both kaolinic clays and bentonite or montmorillonite clays. So a little bit on the naming of these, since we have so many materials that are very similar in composition, or at least the reactive components. The commercial CK, so CK would be the calcined kaolinic clays. So that would be the industrial calcined ones are labeled commercial. There's two of them. And then the C corresponds with the supplier location, which in this case is the central US. The laboratory calcined ones would be CKC again, so for calcined kaolinite clay, and then the central US. And then in the cases like in material composition and characterization, the uncalcined version of the raw clay that we calcine in the laboratory is labeled just as KC. And then with that, the CW and E correspond with the supplier locations across the low US of Central, West, and East. And then the Class F fly ash and the commercial metakaolin are used as a control and a comparison because we're a little bit more familiar with those materials traditionally. So the lab calcination temperatures that were done in our laboratory were for the kaolinic clays, they were taken to 650 degrees C, held for 1 hour, and then taken back down to room temp. And the bentonite were at 830 degrees for an hour. So this just shows the wide geographic region with these clays. It's important for transportation costs and for just developing a green material and saving on CO2 emissions. That's using what's more locally available. So the bentonite clays are down in the Texas region, and then all the rest are the kaolinite-based clays. So just a brief material composition by XRF. All of these materials satisfy the chemical requirements for Class N of ASTM C618. And with that, one important thing is kaolinite content for these clays and their influence on reactivity. So the goal was to obtain a wide range of kaolinite contents. And we did do that with the 24% all the way up to 85%. So it was shown that the 85% may not be considered a moderate purity clay anymore because it's pretty high purity, and at least in the reactivity data was closer to metakaolin. But this around 65% is definitely moderate purity kaolinite, and then 24% is on the lower end. So the other phases present for the higher purity ones is muscovite, and the lower purity is mixed with quartz. So to test the reactivity, the chemical reactivity of these clays, the R3 test was used, which is the rapid, relevant, and reliable test method. So in this method, a Portland cement system is simulated using calcium hydroxide, calcium carbonate, and a potassium solution. So there's two components. There's isothermal calorimetry, where the sample is cast and run for 7 days at 40 degrees C, and the heat release is measured. And then also a bound water component, where after those 7 days, the weight loss is measured in a furnace at 350 degrees C, and this is to measure the chemically bound water. So this is your typical results from this test, doing both the components. The bound water is really just to gain chemical reactivity insight with simple equipment. You can see on the right that these two values with the 7-day cumulative heats and the bound water pretty well linearly correlated. So that would say that, this test, you can use either or. And you can see that fly ash is at the bottom, and the commercial metakaolin is at the highest chemical reactivity, which is expected. So from here on out, it'll just be about the isothermal calorimetry, not the bound water. So this is the full cumulative heat graph. And again, the metakaolin is at the highest end, and then the CKE1. So that's that 85% Kalonite content from in the eastern US region. So that has a much higher reactivity than the 24% Kalonite content down in CKW2, which is expected. And the CKC and CKW1 are those 65%. So they're right in the moderate range. And that's just to show this Kalonite content again. It's largely dependent on the heat. The heats are largely dependent on initial Kalonite content, which is expected. So we definitely are seeing that trend. So the bentonite clays, so here we have the two bentonite clays that the supplier is from Texas, and also a fly ash as a control, and the MKC, which is one of the moderate purity clays. So this is really just showing that these montmorillonite-based clays are also reactive and could be used as well, if they could be viable if that's what's locally available. So the sodium bentonite, which is CBT1, it was less reactive, which agrees with previous literature with Hollanders and other authors. But both of these materials are reactive compared to the moderate Kalonite clays. So to determine workability, I use the mini slump test, which is just a smaller version of the general slump test at 60 millimeters instead of the full height. And here you can use paste instead of concrete, and also not the mortar flow because didn't have quite enough material. So paste was used with the mini slump test. This test was performed at a 30% cement replacement and a 0.5 water to cement ratio. And this was really just to determine the difference between the metakaolin, which is well known in the field, versus these moderate calcined clays. So the results are here. We have OPTC on the very left, and then the next three are all of the moderate purity Kalonite clays, calcined Kalonite clays. And then the definitely the worst workability was metakaolin, which is expected, and then class F fly ash, the best influence on workability. So for those two in particular, you wouldn't really use 30% replacement traditionally. So the results are a bit inflated there. But yeah, so this just shows that the calcined Kalonite clays have similar mini slump to OPC, so wouldn't have that major impact on workability that you see traditionally with metakaolin. So just a little bit more visual. The metakaolin was on the left, and this wasn't quite a valid test because I actually had to scoop it into the actual slump cone. And then we have OPC in the middle. And again, this is a 0.5 water cement ratio and the moderate purity calcined clay. So that was the 65% Kalonite, just like the true moderate one. And those were very similar. And then your most workable of the class F fly ash. So in conclusion, the higher Kalonite contents correspond with increased chemical reactivity in the R3 tests, which was expected. The calcined bentonite clays show R3 values within the range of moderate purity Kalonite clays, suggesting that these clays are also good SCMs. So in the event that those are close to you, that could be a viable option. The R3 test outputs indicate moderate purity clays are reactive and may offer a significant benefit as SCMs. And the minislump results suggest that these clays will not have a significant impact on workability compared to OPC. Thank you for your time and attention.
Thank you so much, Caitlin. That was really nice talk. We do have one question already. Let's see. So the question is from Pranoy Saraneni, University of Miami. And he asks, in the R3 test, the heat release or bound water correlates with the Kalonite content. The values for highly reactive metacalins are around 1,000 joules per gram of SCM. So even a clay with a 30% Kalonite content or low purity is about as reactive as a fly ash, which is about 300 joules per gram of SCM. Would you expect the same durability benefits from such a low purity clay and a class F fly ash, broadly speaking? So you didn't really touch on durability in your talk today, so I don't know if you want to extrapolate there, but he's basically asking for impure clays, how does the performance compare to fly ash?
Yeah, so I haven't done any durability studies like on my own, but I know there's quite a bit of literature review that says that it is comparable durability performance. I think there is still room for research in that area, but on the I'm not sure. So the low purity, like the 24%, I think it's been shown that those aren't quite comparable, even with a strength like that. That's under the threshold for what you get, like comparable for performance. But yeah, so I haven't done any studies particularly, but I know that there have been done.
Okay. Great. And then to keep us on time, I'm going to combine the next two questions, and there's going to be some more that you might want to go and check in the Q&A after we start with the next speaker. But I'll combine these two, both compliment you on your presentation. One asks, what were the colors of the Kalonite samples used? And another asks, was the RM325, what was that? Was it raw?
Oh, so the colors after calcination, the 85%, those are pretty white. So I think would be like a pretty pure material, more comparable to metacalin. But the other ones, I have some pink colors, some like bright pinks, some like brownish. So all different minor impurities that affect those colors.
Thank you so much, Caitlin.
All right, thank you.